In this video, we'll look at a couple more examples on the step function and the t-shift in Laplace transform. We will start by looking at a more complicated step function. From 0 to 1, it stays at 0. From 1 to 4, it stays at 1. And from 4 to 6, it stays at -1. And 6 onwards, it stays at 0. There are 3 transitions here as being labeled on the figure, and we'll look at this one by one. And the question is how we can write these as step functions. The first transition happens between 0 and 1. In step function, it's written as u t minus 0 minus u t minus 1. We start from 0, we finish at 1. So we use t minus 0 minus t minus 1 in step functions. For the second transition, it happens between 1 and 4. So in terms of the step function, we write u t minus 1 minus u t minus 4. And the last transition happens between 4 and 6. Not surprisingly, the step function will be written down as u t minus 4 minus u t minus 6. Before moving on, I'd like to draw attention to the coefficients we put in front of each transitions. In the first case, from 0 to 1 is at 0, so we multiply the step function by 0. In the second part, the magnitude is 1, so we multiply the step function by 1. And lastly, from 4 to 6, the magnitude is -1, so we multiply that transition or segment by -1. The first part is simply 0, and the rest is very simple. In the end, you will have the step function written down as u t minus 1 minus 2 u t minus 4 plus u t minus 6. And this is your final step function. In the second example, we'll look at t-shift with a somewhat more complicated step function. In this curve, from 0 to 2, it stays at 0. From 2 to 2 pi, it's at 1. And from 2 pi onward, it's a cosine function. If we write down the expression of the function, ft, it equals to 0 if t is greater than 0, less than 2. It is equal to 1 if t is greater than 2, less than 2 pi. And it is cos t if t is greater than 2 pi. And what we want to do is to calculate the Laplace transform of ft. Again, here we have 3 transitions or 3 steps in the equation. So we'll start by writing down the step function. The first part of the step function is from 0 to 2. Since the magnitude is 0, we'll not write that down. For the second part, the magnitude is 1, and it's between 2 and 2 pi. So the step function can be written down as u t minus 2 minus u t minus 2 pi. For the third part, the magnitude is cos t, and the step function is 2 pi onward. So the step function will be simply u t minus 2 pi. Since there's no upper bound, it goes into infinity, so we don't have to minus anything here. And this is our ft. Let's simplify ft a little bit. And now let's recall what we have learned in the last video. The first is the Laplace transform of the step function. Laplace transform of u t minus a is equal to e to the power of minus as over s. The second is the t-shift. Laplace transform of f t minus a times u t minus a is equal to e to the power of minus as, then capital Fs, where the capital Fs is Laplace transform of ft. The third equation is new. We're not using it here, but I think it's good to know it. So Laplace transform of ft times u t minus a is equal to e to the power minus as, Laplace transform of ft plus a. The rest is pretty straightforward. The first 2 parts, these are step functions, so you can just use e to the power of minus as over s. The third term is a little bit tricky. We'll use the second formula here. For the step function, it's u t minus 2 pi. We want to make ft, the cos t, in the format of cos t minus 2 pi. Luckily, for cosine functions, t minus 2 pi is itself, so we can just simply write cos t minus 2 pi times u t minus 2 pi. Then you apply Laplace transform to it, you get e to the power of minus 2 pi s, then s over s squared plus 1. S over s squared plus 1 is what you get if you apply Laplace transform to cosine t function. After looking at the step function in Laplace transform, in the next video, we'll look at a new special function called the delta function.